All right, line A4, learning task 10. We're going to talk about the application of capacitors for power factor correction. In other words, where are we supposed to place them and why? So when we do connect in a capacitor, the first thing that we need to remember is that we're working inside of a standard system where we don't want to have all components dependent upon any other single component, which means that we're going to be using parallel connections. We could use a series connection if it is done correctly, but there's always danger in doing a series connection. Plus, if you lose your load or your cap for either reason, you're going to go and lose the other one as well. What we don't want to do is we don't want to ever accidentally place anything in series and create that series resonance, because as soon as we go into that series resonance, where I got an inductor and I got a capacitor that are going to be in line, there's going to be a small amount of resistance that's going to be across that inductor there. If I did manage to make my XL equal to my XC, and we can talk about XL and XC right now because we're talking about series circuits, but if I did make them the same, what would then happen for me is that I would have absolutely no impedance in the circuit other than a tiny little bit of resistance that's going to be caused by my actual inductor, which means I'm going to get really high values of voltage over top of my components. In fact, they can be higher than what the dielectric is designed to go and withstand on the capacitor, what the insulation is going to be across my inductor. It's just going to result in this thing to be destroyed. It's going to melt down. So we do not want to go into series because of that danger for that series resonance circuit. Instead, we want to go and deal with stuff in parallel. We're going to connect them in parallel with one of three things: either our main, a group of smaller loads, or an individual large load. Once again, going back to that BC Hydro piece that you had over there, if you go down that BC Hydro one, they talk about diagnosis, etc., and then methods of correction that we could go and use. And they give you this drawing over here. It's a one-line diagram. You should be familiar with reading one-line diagrams at this point. Basically, it doesn't show every single line. It just shows that we got, power, all the lines of the neutral coming in, etc. Couple of places that they can be applied. First of all, they show we got a transformer. It's a 12 kV down to 480 volts. This is my incoming. Here's my circuit breaker over here. Here's my metering. And they're showing that one of these places we could do it is we could apply a large cap. That's a circuit breaker in front of it, the symbol for it. And there's my cap at the service entrance. The other place that we could do it is we could do it downstream. So here I'm moving out of my service and I'm going over, and I've got a circuit breaker over here that's going to go and apply it to a bus. That's going to be this whole section over here for my motors. It's a group of small motors that I'm going to go and have operating together. The other place that I could do it would be to go and apply it directly at my motors. It's hard to see, but it's just tapped off the side over there that I've got 50 horsepower, large horsepower motors, and I'm going to go and take this thing directly off of the tap over there. They talk about these methods, over here. For motors of 50 horsepower and above, it's best, it just wants to jump from page to page. Let me just see if I can just pull this one up just a hair. There we are. So we can actually see what's going on there. 1 second, it's still a little bit janky. Trying to get the whole page on there. Oh, for Pete's sake. Perfect-ish. Just shorten that one up there. Okay, so for motors of 50 horse and above, we want to directly put them at the motor because it's going to go and drop the line current all the way to the motor. That means that the voltage drop to the motor, the VA of the motor, all of that stuff is going to go and be dropped. Now, we can place it downstream of the contactor. If we do place it downstream of the contactor, between the contactor and the motor itself, we are going to have to adjust our overloads for that. They talk about that inside of here. They talk about that inside of your module as well. The second place is where I'm going to go and have it connected for a bus. So they talk about this over here where I've got multiple smaller motors that add up to become about 50 horse, and I'm going to go and bus connect. In other words, when this bus gets energized, I'm going to energize that cap over there. There is danger, though, that if each of these small motors that get shut off and this cap stays on, that I could end up with a leading power factor. The last one that they have is the least expensive. It would be for me to put it at the service entrance. However, if I do go with and put it at the service entrance, I need to be very careful that I'm not going to go and put it into overcurrent action. You don't want to have just a single large cap. What you want to have is a group of smaller caps that are going to go and be switched on and off automatically, etc. Okay, let's take a look at what our module has inside of it. The module basically reiterates a lot of what we're seeing inside of that hydro one. They show us an individual load connection over here where I've got a large motor that is going to go and be connected. Over here, I've got a disconnect switch. I've got this capacitor that is then going to go and switch out to the motor itself. We do have to be careful when we go and place them inside of here. And let's just talk about where the motor contactor itself should be. You should be familiar with motor contactors from first year. You know, the motor contactor is just going to be that device that has got two sets of contacts that is shown open like that. And when I power them up, it's going to go and apply power to that motor. It's going to be my electrical switching of that motor. Now, if I place my cap downstream, all the way over here, I have to be very cognizant of my motor overloads. You should have had those explained to you inside of first year as well. But motor overloads are simply going to be current responsive devices. Downstream of my contactor, my current goes through. Here's my disconnect switch. Here's my contactor. And then it's going to go through this set of overloads over here. And what these overloads are designed to do is they're designed to heat up based upon motor current. And if they get too hot, they're going to go and trigger a little bimetallic strip that's going to be inside of my control circuit. That bimetallic strip is going to go and be tied into my controls to open this set of contacts, basically shut it down. What's it doing? Well, it's monitoring the current. Too much current goes through, creates too much heat, trips the switch, shuts the motor itself off. It just prevents us from burning out motors. This is sized based upon my motor's amps. There's going to be a whole thing inside of section 28 of your code book on how to go and size that. Now, as soon as I do power factor correction, what happens is I change my VA of that motor. Which means that if I size off of the VA of the motor, that means I'm going to have to go and reduce the size of my overloads. It's not a bad thing. It just means that you need to be quite aware of how you are doing this so that you don't, end up leaving your overload set to the original VA, which would then be too high for that motor itself. The other place that you could be placing these in would be upstream. So it's still downstream of the contactor, but I could go and place my cap in right up there. And if I would do that, then what happens is it gets applied, but I'm only going to go and have the full motor current, the full VA that's going to go through this, which means that then I don't need to go and downsize these ones. It's a little bit more tricky to do because in a lot of cases, the contactor and the overload are built together. But if you do have the option of doing an individual large load connection and you can go from an individual contactor to a standalone overload, that would be the ideal place to put it because that way you can match this to that. Otherwise, you just have to do some additional mathematics. Once again, this is always going to be dealing with a single large load that we would be dealing with this. I see as well that my cap is only going to be online when the motor is online, and it's going to be offline when the motor is offline. You would not want to go and place that up over here. If you were to place it like that, then as soon as I switch the motor off, I lose my inductive bars, which means I could go into that overcorrector leading power factor and raise my terminal values of voltage. Excuse me. Too much talking. Feeder correction. Feeder correction is where I'm going to go and have multiple smaller motors. We saw that inside the hydro handout there as well. But where I'm going to use one power factor correction capacitor to go and correct a whole pile of motors. Sometimes it'll be done with multiple smaller ones as well up here, so that as each of my individual ones come on, I just go and correct that feeder. Then I don't need to go and have these things dropped all over the plants by my motors or anything. I just have them all as a central grouped hub inside of my electrical room. Some cases, they're actually going to be applied already at it. Then it's not us doing power factor correction, but if you take a look at ballasts, any type of lighting ballasts themselves are going to oftentimes have that lagging power factor if they're an inductive type. They're going to have a cap inside of them. They'll be corrected. They'll usually note that on there. Main service can also be corrected. Where I've got my incoming power coming in from BC Hydro, and I'll have a switchable bank of correction capacitors. Now, what we're not going to see is a giant honking capacitor. Okay, don't expect to see something that's going to look like a oil drum or something over there. That would be insane. We're going to have smaller square capacitors, and usually what they actually end up looking like is it's just going to be another big gray steel box. Right? We're used to our services being these big gray steel box. Inside of that big gray steel box, we're going to go and have a whole pile of smaller individual caps. And each of these individual caps is going to be outfitted with a single contactor. that's going to be on there. Let me just finish putting all these in. So each of these is a cap and contactor combo. All that we do is we take in our main line lugs. So we'll just take in a red, a black, and a gray for my neutral. And then we take them back out of this one as well. Obviously, it's going to be inside a conduit or something like that. I'm not crazy. We're just drawing it simple over here. So I've only got 3 lugs to go and bolt onto. 3 lugs on the incoming side, 3 lugs on the outgoing side that I'm going to go and bolt into. Or in some cases, I don't even need to have that. I just have a single set of 3 lugs and I tap off. I tee off my main conductors to go down and into it. It doesn't make much of a difference to us which one we're going to do. The last thing that we see on most of these is that they're going to go and have what we refer to as probes. They're going to be current sensors. They're basic ammeters that are going to be connected. Inside of here, there will be some sort of a brain, a microcontroller. You see, microcontroller that we're going to have. That brain is going to get fed by a bunch of probes. So when we make these connections in here, particularly on the kind of where we go in and out, I don't need to make that connection because it's already going to be done on the inside. Why don't I actually draw that because that's the simpler one to go and envision. Inside of here, this thing is just coming up and across like that. Same with this one, coming up and across, and this one up and across. But inside of there, that microcontroller has got an ammeter around each one of those lines feeding back to its brain. It's also going to go and have a voltmeter. It's going to be reading the voltage on each of those lines. And then what it does is it just continuously monitors that power factor. It's able to see where the current is compared to the voltage. And then based upon that, it can then say, you know, I'm leading or lagging, and this is what I need to do. What it does is it continuously monitors as I add more loads on inside, it's going to go and switch on more caps to compensate. As I turn loads off inside, it's going to switch them back out. It is an automatic type that is going to be used. It is very rare that we're going to go and have manually applied capacitors because what we would need to have is a plant operator who would be sitting there watching. Large industries, you know, huge industries, power plants and stuff like that will actually have, you know, operators. Their only job is just to operate the system. They sit there, they watch the dials, they switch stuff in and out. That's their job. But in a lot of smaller ones, you know, we just do this manually itself. All of my caps are going to go and have nameplates on them. A lot of my power factor industrial capacitors are going to be square capacitors. They're usually going to be made out of plastic. On the outside, we don't want to have them made out of metal necessarily. They'll be made out of plastic on the outside. They're going to go and have the plates inside, the dielectric. It's usually going to be like an absorbed glass mat type of dielectric inside of there. And they're going to have ratings on these things that are going to be always the following. Voltage. We need to know the voltage because if we go too high above the voltage, we're going to go and blow out the dielectric, right? The maximum dielectric strength. If it says it's 600 volts, we can put that thing onto a 600 volt system. The voltage rating is always going to go and be an RMS type of rating. The second thing is we're going to go and have our VARs that this thing is going to be. Now, they're not going to go and put it into microfarads or things like that. They might have it mounted on there. They might tell you what this thing is for microfarads, but they work under the same assumption that I do, which is that once you leave, you promptly forget everything from school, and you just know that the VARs have to go and match, so you're going to go and match those VARs because you don't remember how to do that, you know, 1 over top of 2 pi root L FC formula for your capacitance anymore. So they just say, look, it's going to be difficult for our electricians out there. We'll just rate this thing inside of VARs instead of farads. It's going to be rated as well for frequency. These are going to be my top 3 ratings that I'm going to have. You need to make sure that the frequency is correct. If you go and change frequency, if you use something that is rated for a 50 hertz on a 60 hertz system or 60 hertz on a 50 hertz system, it is going to go and screw up the capacitance. This is very critical on pieces of imported equipment. Sometimes you're going to get customers that are doing something special. I don't know, you know, they've got just an industry where they buy special equipment. A lot of our agricultural equipment in the Fraser Valley, we get a load of it that comes out of Holland. We get a lot of mining equipment that comes out of South America and out of Asia as well. So we're going to have places that are going to be 50 hertz systems where people are going to buy something. Your customer does not know what a hertz is. Guaranteed. They're going to go and buy stuff because they're going to say, hey, this machine is able to do X, Y, and Z. And they'll be like, perfect, I'll buy it. And then they get it to you, and then you're like, but this thing's rated for 50 hertz. Don't go hooking it up because the VARs of all components inside of there are going to go and be different. Hopefully your customer consults with you before they go buy crazy pieces of equipment, but if they are buying from overseas, yeah, be very careful, especially if you get a customer that sends you something, a nameplate, and they say, hey, I'm looking at, buying this piece of equipment. Could I put it in? Don't do the 3-second, look at it and be like, oh yeah, it looks good. Make sure you're checking the frequency. If it does not have 50/60 that it can operate on either, or that it's got an available model that's rated for 60 hertz, don't go for it. Okay? You don't know what's inside there until you actually get a chance to poke around. And if you tell your customer to buy it and it doesn't work here and you have to pay to go and make it work, that can get really costly. Okay, those are my 3 main ones. The VARs, the volts, the frequency. Sometimes I am also going to go and have the amps that are going to be rated. If I give myself a rated amount of amps to this thing, that's just going to go and help me size my conductors that are going to be going in and out of it. It's useful. You should be able to go and calculate it off of this. Once again, VARs is a form of power, so you should be able to go and take your voltage and your VARs, and you should be able to divide out and figure out your amount of capacitive current that you're going to have inside of there, and use that one. Let's talk about the changes that could go and happen as we change values of frequency. First of all, we're just going to go straight to our formulas, and we're going to go and show what happens from component to component over here. We're going to work backwards through a couple of formulas over here. We're going to relate them, the XC, the VARs, etc. So I'm just going to start with this one over here. XC is equal to 1 over top of 2 pi FC. We're going to start with that one over there, and we're going to go and see what happens when we change our value of frequency across a piece of equipment. Now, we're working in BC. So it is unlikely that you are going to go and end up working somewhere on a 50 hertz system. We don't have those inside of BC. You are going to be working on 60 hertz systems, which are then going to go and have, if we take a 50 hertz piece of equipment, we're going to find some stuff that's going to go and happen. Let's start with this 50 hertz piece of equipment. You get a customer that sends you something, a capacitor, that is going to be rated. It's got some rating. It's going to be at 50 hertz. And they're asking you to go and apply that onto the system. Now, that capacitor is going to be rated in its VARs that it's going to go and have, right? Those VARs are developed by, even if it's the same value voltage, let's say it's a 600 volt one, I've got VARs that are a form of power. Power is equal to my E squared divided by R, right? Except in this case, my form of power is going to be my VARs. And my form of R is going to be my XC that I'm going to have over here. So we're going to find out what happens to my VARs when my XC is going to go and change. And my XC is going to go and change because we are going to have increased, right? It's rated for 50, but we're now going to go and scab that thing onto a 60 hertz system. If F, my frequency, goes up, so this equipment was designed, now we're increasing the frequency of it. That means that the XC, the capacitive reactance of that equipment, is going to have gone down. If my XC goes down, that means that my VARs, remember this is an inverse relationship over here, is going to go up. So whatever I go and put onto this thing is going to go and have a overcorrection. We're going to go and have more VARs out of it. Now, it could be that's a good, useful amount of VARs. That's fine. But we would still not want to necessarily do it. First of all, this thing has been engineered for 50 hertz. 50 hertz just means it's a slower back and forth movement. The dielectric, the amount of heat, all of that has been based upon the fact that those individual orbitals are going to be going back and forth 50 times a second. Now we're going up to 60 times a second. You change from 50 reps of anything in the gym to 60 reps of anything in the gym, you feel it. So does the dielectric that's going to be inside of here. That is going to go and possibly create, overheating. So it's just bad form. Yes, you can calculate. Possibly you can go and use it. But you're going to go and end up at some dielectric heating that's going to go and happen. They show a example inside of the book over there where they go through all the math of exactly what these things are going to go and be. And how much that it's going to actually increase the amount of current feeding to the bank, etc. as well. Because our VARs have gone up, therefore the amount of capacitive current is also going to have gone up. Voltage has stayed the same, right? Voltage changes are also going to go and make a difference. If I go and connect something to a larger value of voltage than what it's supposed to go to, I'm going to obviously blow that thing up. Now, we're not going to take a look at that because only an idiot would go and take a, something that's rated for 208 volts and put it onto a 600 volt system. But sometimes stuff happens where people will say, well, I've got a capacitor, we'll say that's the right frequency now, and this thing is rated for 600 volts. I want to use this thing on my 480 volt system. Can you do it? Absolutely you can. You're not going to break it, and you're not going to go and overheat the dielectric from that, back and forth too fast. What we are going to see, though, is we are going to go and see a reduction in the total amount of VARs. That rating that this thing had in VARs before is going to drop because what I'm seeing is I'm dropping my value of E squared, which means that I'm going to drop my value of VARs out of this thing. Once again, you would just have to go through a set of calculations. You can use them on a lower value of voltage, but you're just going to get less VARs out of it. It's not going to be a direct relationship. It's going to be down, by squared type of relationship. You can go through the examples inside of the binder off of this one. They go through some math just showing, that there's problems that happen when I increase the value of voltage. I'm not going through the one on the increase in value of voltage because I think it's absolutely ridiculous that I need to explain to you in second year that putting something to too high of a voltage is going to be bad for you. You understand that. I understand that. Just don't do it because it's going to go and cause problems. All right. That is through Self-Test 10. Go through that BC Hydro folder if you have not had a chance to go and do that. Make sure you do that as you go through. They give a couple of explanations, once again, on calculations and things like that. You can have tried to go and use the chart to do it, but we're going to go and use the maths to go and do our power factor correction. And we're going to move on to that now in our next